Okay, great. All right, so what you are going to need to have today, starting out with, is you're going to want a fresh blank piece of paper. You are going to want to have a pencil. Nate, you're not going to need your laptop, so the laptop can go away. And what I would like for everybody to do first,
will this be something we turn in, or could it be like a notebook, please?
this can be a notebook thing. So this will be a tool that you will be using to help with the next assignment, and actually something that we're going to be using quite a bit. Okay. So what I want you to do is start by marking a point roughly in the middle of the paper. It doesn't have to be exactly in the middle. And that I want to serve as the starting point to do that. For just kind of a generic right triangle. And it's not an arbitrary instruction to start roughly in the middle. This will help to get the notes placed sort of in the right place around it. Okay, so one of the problems that we have right now with trigonometry is that we are limited to what is the biggest that this angle could possibly be?
89.
Wow. So yes. So it could, if it was a 30, 60, 90 triangle, we could have the 60 degrees down here. But we could keep going. We could, yeah, in fact, we could open it up, and this is just kind of like a separate little side note. You're welcome to put this on the bottom of your paper if you want to. But we could, in theory, have this very sort of shard-like right triangle, where this is 90, this is 89, and this is 1 degree. In fact, is 89 degrees even actually the biggest?
No.
Because what else could we have?
90.
Well, if we have 90...
89.9.
we could have 89.9, 9, 9, 9, 9, 9.
Keep going forever.
But all of a sudden, if this is 90 degrees, then we either have something that looks like this, which is not a triangle.
Why not?
Or... yeah, it looks kind of like a really badly drawn elephant foot. I'll give it its other little. But we run out of sort of possibilities because there's only 180 degrees in a triangle. Okay, likewise, what's the smallest that this angle could be?
0.0000.
Yes, so we could think of like an incredibly shallow right triangle like this, where this is 1 and this is 89, or this keeps getting smaller and smaller and smaller and smaller. And it's like the triangle is slowly just sort of, it's like it's sunsetting, it's just collapsing down, 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 down. And so this is the problem, this is one of the problems that we have right now with trigonometry. We're basically limited to angles between 0 and 90. So it's not even really that we're limited to 180 degrees out of 360. We're actually limited to between 0 and 90. We can only cover a quarter of the circle. So that is very limited. And there's no way that I'm going to make good on my promise to you that trigonometry helps us to explain the transmission of all information across the universe if we're stacked between 0 and 90 degrees. So we have to figure out a way to break out of that. Okay, the triangle actually goes on sort of a hero's journey. And actually, the way that the triangle breaks out of its 0 to 90 degree confines is by connecting to its origin. Connecting to the origin. Taylor is appreciating this. So actually, the first thing that we're going to do, how we're going to help the triangle to break out of its 0 to 90 degree prison, is we are going to place it specifically at the origin. In order to set it free, first it has to go home.
This should be a movie plot.
Oh yeah. It really, I mean, it is incredible. As we continue with this, in fact, we're going to see another great sort of, if this is the inciting incident here, it finds its home. We're going to get to plot point 1 really quickly here. And part of what happens, you know, and you guys have seen plenty of movies with a great origin story. Part of what happens when you go back to your origin is that you probably learned something negative. Maybe you are able to connect to your alter ego, or maybe your dark side. How is it that by putting a triangle at the origin, how is it that we have introduced the concept of negative numbers or something negative? Yeah, Quinn.
By putting it on the graph, it gives the context of this is not just numbers, they're positive numbers that exist around negative numbers.
That's right. So this is a very clever trick where suddenly we've opened up, now we have all real numbers. We used to just have, all we had here was positive integers. So we just had, in fact, we only had, and in fact, here's the 0 to 90 degrees right here. We only had this quadrant because we could only have positive legs of the triangle. But now that we have a context, and the other trick that we do is we set this direction right here to be 0 degrees. Those aren't little fish bubbles, 0 degrees. And we think of the hypotenuse as being on a hinge at the origin that we can rotate. So it's like we've got this movable hinge that now we have stopped here at this angle. But if we can move it from 0 up to here, or we can move it from 0 to 90, we can keep going. And so we can also think about this guy. Now he can see his reflection over here. So we can create the identically proportioned triangle. But now we have created it, we've moved into negative territory by going past 90 degrees into an angle that is greater than 90 degrees. So this, another way to think about it, again, as we're developing the script for this film, maybe this is the moment, stepping through the mirror. Almost there with its reflection. All right, so let's say, so we know that this, because this is a right angle, we know that this is 90 degrees. let's say that here, this angle is 60 degrees. And we want to figure out what angle this is if we've created the exact reflection. The first thing that it will help us to do, helpful there is, let's say that we just keep going all the way back to the horizon. How many degrees is this pointing this direction? Yeah, Kate.
180.
This is 180. So if we kept moving the hypotenuse all the way down here, that would be 180 degrees. If we've created the exact reflection, yes, Quinn?
Could, can I, like, say how I would?
Yes.
Because it's 180 degrees, and you know that one's 60, and you know the other one is an exact replication, couldn't you just minus 120, or 60 plus 60?
That's right. So
And-
it's, exactly. So now it's like we're stopping 60 degrees short of the 180. So we can, so that we can stop at 120. And in fact, that is what this angle is. So this angle here, this is a triangle that we've created that technically has an angle that's 120 degrees. All right, somebody give me a nice number for the length of this hypotenuse. Yes, Kate?
32.
Okay? So that's a nice number. So we say the hypotenuse is 32. If this is an exact replica, what is the length of the hypotenuse of this triangle?
32.
Also 32. What is, and I have not drawn this to scale, so we gotta make sure that we're checking correctly, but if this is 60 degrees, that means this is 30 degrees. So what is the length of the base of this triangle then? We've got a 30, 60, 90 triangle. I see your hand, Cade. Yes, Alex?
16 square root of 3.
Across, well, we gotta,
Oh.
again,
Oh, no, wait. Oh. Huh.
yeah, the
Okay,
base.
it's just 16 then.
So this is gonna be 16. Remember, it's the side across from 30 degrees that's half the length of the hypotenuse. And then in a 30, 60, 90 triangle, what's the length of the third side?
16 square root.
16 square root of 3. Okay. So we've labeled this 30, 60, 90 triangle. If it's an exact replica here, then what's the height of this triangle gonna be?
16 square root 3.
That's right. Okay, but now here's my question for you, Taylor. Given that we are in the XY coordinate plane, and given the position of the base of this triangle, what is the length of the base of this reflected triangle?
Wouldn't it also be 16?
Its absolute value is 16, but this has a position in the coordinate plane, which means from here to here is negative 16. So we've kind of suddenly, again, by bringing the triangle home to its origin and letting it sort of step into its reflection, we've sort of managed to just sort of jailbreak it in two ways. One, we can have an angle like 120 that we can't have in just a normal triangle that's just sort of floating out in space somewhere. So we've introduced degrees beyond 90. And number two, because we're in the XY coordinate plane, we've also introduced negative numbers. So this one little trick of anchoring the triangle in the XY coordinate plane and having the hypotenuse, thinking about it like it being rotatable on a hinge, we've suddenly blown wide open the possibilities for this triangle. Okay, So what is, so here, and well, we're gonna label a couple other things here before we get to the next part. We label this quadrant 1, and that makes sense because that's the normal place that we've started, where all the angles fit inside a regular triangle, all the sides are positive, and everything is familiar. So this is quadrant 1. That is, yep, Taylor's giving me the 2 sign, and that is correct. This is quadrant 2. But do we have to stop at 180 degrees? No, Taylor's flashing me the 3 sign, the keep going sign, yes. So we can keep going around the circle. This is quadrant 3. Yes, I'm getting the quadrant sign from Kate as well. This is quadrant 4. And they are quadrants because they are fourths of the plane. So we can do a little bit of a reminder here, sine of, well, actually we're going to go ahead and do the angle. The other thing to note is that the angle that we consider is always the angle that is next to the origin. So technically this triangle has both 60 degrees and 30 degrees. But to keep ourselves organized, the trick that we're going to use is we're always going to be talking about the angle that is centered at the origin. So this helps us to stay organized now. So when we're looking here, so cosine of 60 degrees, cosine is adjacent over hypotenuse. On this particular triangle, what's the length of the adjacent? 16. So we've got 16 over 32, which equals 1/2. But now we've got its reflection over here in the second quadrant that has the same proportions. So here, the cosine of 120 degrees is going to be adjacent over hypotenuse, although I will grant you, at this point, it's starting to become a conceptual adjacent, because we're considering the length of the side that's on the triangle, but actually the angle is this exterior angle here. So it's become a little bit more conceptual than direct. So it's going to be negative 16 over 32, which is going to be negative 1/2. So let's go ahead and confirm this on our calculators. And we are going to put in cosine of 120 degrees. Check to make sure that your calculator is in degree mode. But what do you get when you calculate the cosine of 120 degrees? Negative 1/2. Delightful.
Should our calculator be in like degrees mode every time we use cosine or
For now, yes. So in the same way, kind of like how with lengths we have feet and meters, and then we also have other more archaic things like leagues and lesser known measurements of length. We also have 2 measurements of angles. We have degrees and radians. And radians we will also be learning to use. But right now, everything that we're doing is in degree mode. All right, so let's go ahead and keep going, using your same logic, Quinn, now when we keep going past 180 degrees, where are we going to stop in order to create another identical reflection?
Wait, what was the question? I'm sorry, I was writing it down.
Yeah, no problem. So when we were asking the question, okay, what is this angle going to be when we create this reflection here? You said it was going to be 120 because it was like we were going to stop 60 short of 120.
Mhm.
Using that same logic, continuing, what's our angle going to be here?
Right there?
Yes.
30.
Well, I should say,
For that
you
corner.
were correct. This angle will be 30. But if we're thinking about continuing to move the hypotenuse and stopping it here, how many degrees have we gone in total from 0 to stop here?
240?
That's right. Is that what you were going to say, Kate? Yep, sorry. So that's right. So that's 120. And in fact, I'm going to go ahead and label them out here because it's starting to get a little bit crowded in here. But this is 60. This is 120 because we're stopping 60 short of 180. This is 240 because we're going another 60 after 180. All right. If we've created sort of an exact reflection, Jasper, is the length of the hypotenuse going to change, or is it still going to be 32?
It'd still be 32.
That's right. So the hypotenuse hasn't changed, the hypotenuse is still 32. We can see here, this is even just the same side, so this is still the same negative 16. But, Nate, what is the length of, normally we would say the height of the triangle, but here this is almost more like the depth of the triangle.
Negative 16 square root of 3.
That's correct. So we can now see that in quadrant 3, both sides of both legs of the triangle are negative, and so that is going to impact both adjacent and opposite. They're both negative. So we can go ahead and put here too, cosine of 240. This equals adjacent over hypotenuse. The adjacent hasn't changed, the hypotenuse hasn't changed. It's negative 16 over 32. This is still negative 1/2. All right. So Alex, to complete our little bow tie here, what angle are we going to stop at in order to create the last reflection of this triangle in the fourth quadrant?
It'd just be 360.
Well, if we stop at 360, if we bring the hypotenuse all the way back to 360, the hypotenuse will be kind of like right here, right matched up with the, because so 360 will be going all the way around the full circle. By the way, what will the angle be for, what's the angle for straight down?
270.
270. Oops, not 370. 270. But if we want to keep rotating this hypotenuse around on its hinge, where will it stop to create a reflection in this triangle again in the fourth
Oh,
quadrant?
I see. 300?
That's right. Because we're going to stop 60 degrees short of the full 360. All right, and here we can see we've already got the adjacent side labeled. It's the 16. What is the depth of this right triangle, Alex?
Negative 16 square root of 3.
That's right. And has the length of the hypotenuse changed, everybody? No, it has not. So we can think of it as being the exact same hypotenuse that's just rotating around. And so here we can see the cosine of 300 degrees, adjacent over hypotenuse. Here we've got 16 over 32, and we are back to the cosine being equal to 1/2. Okay. One of my students back in the day said, oh, it looks like a bow tie. So now I often think of this as the bow tie of trigonometry. What I would like you to do now on your paper is to also find the sine of 60, the tangent of 60, the sine of 120, the tangent of 120, the sine of 240, the tangent of 240, and the sine of 300, and the tangent of 300. Now you might automatically think it's like, oh, okay, well they're negative over here, and they're positive over here, because that's what we saw with cosine. But I want you to be really thoughtful about it. I want you to actually be careful about each of them, and I don't want these to be decimal approximations. I want the actual ratios to be shown, so you want exact answers. You are welcome to work with a neighbor. I'm happy to answer questions, but what I would like for you to do is to continue filling this in, and then what we're going to want to do is simply state the patterns of which trigonometric ratios are positive and which are negative in each of the 4 quadrants. So first we want to calculate these sines and tangents. We've already got the cosines. Then we want to simply describe what the pattern is, which ratios are positive and which are negative in each quadrant. Before we begin, does anybody have any questions right now about what is up on the board? No. Okay. Well, then go ahead and start working on your sines and tangents, and please do, you're welcome to work with a neighbor, compare what you're getting. You're welcome to use the calculator to check your answers, but again, I'm going to want the actual, like for example, obviously the sines, they've got this radical 3 in them. I'm going to expect to see the radical 3 in your answer as opposed to the decimal approximations. Okay? All right, go for it.